And since the train is moving to the right, it's gonna hit those wavefronts first, it's gonna hit these wavefronts first, and therefore the right light will hit first, and therefore Ryan says that the detector's gonna glow green. Peggy, who is with the train car, says everything is at rest to me. Ryan's not, but the train car is at rest to me. If these two things go off at the exact same time, then since they're at rest, they should hit the detector at the exact same time, so the detector will glow red. But only one of them will be right, because after this goes off, after the experiment, they then so after this goes off, they stop the car and they glow, and it's either gonna be green or it's gonna be red. One of them's right, one of them's wrong. So, who's right?
I just run right. Because run right will glow green.
Green, okay, so you're backing Ryan up. Holden?
I'm saying Ryan as well.
Okay?
I'm gonna say Peggy.
Yeah, I'm gonna say Peggy, because it's relative to the detector, and she's moving with the detector.
And the distance between the detector and the two sources of light stay constant.
Yes.
Yeah, okay.
Because the speed of light is constant, so if the detector move close this to speed of light, so it could detect the rise light first.
Wait, hold on just a second, I want to. The distance from the detector to the lights is constant. However, the constant that Peggy sees and the constant that Ryan sees are different. Just want to point that out, because of length contraction. They're not gonna be the same length. So what he sees as the distance between these two and what she sees the distance between these two was not the same. All right, sorry, Kong, I was thinking about that when you were speaking, so please go again, I apologize.
So as in the speed of light is constant, so the detector could detect the bright light first, because the speed of light is constant. So if the detector move closely to speed of light, so it could detect the bright light first, and it will glow green.
All right. I will throw in one other thing, is that we'll just throw, Ryan has a detector also, and the lights hit Ryan at the exact same time. When this goes off, both lights will come, and Ryan will sense that these flashed indeed at the exact same time. All right, so you're still backing Peggy up, you two are still backing Ryan up. Aaron?
I was saying Peggy as well.
So it's a right side, left side part of the room kind of division here, like East Coast, West Coast. All right. It turns out Ryan is actually right.
Oh boy.
But how can that be? What's wrong with what Peggy sees? What's wrong with her reasoning?
Maybe she
She's
lied.
on,
Maybe she lied?
Yeah.
she's on the moving frame.
She is in a moving frame. But why does, well, from her point of view, she's not in a moving frame.
She's moving with the train at the same speed. She's moving with the train. Light is actually, I don't know what I'm saying now.
I think because I'm thinking that too, is she's moving in the direction of the light along with the other light coming this way. I think that's what he's trying.
She's moving,
Because you drew those, like you say, we got light coming from the left and coming from the right.
right.
She's also moving with the light coming to the left.
Yeah, but the speed,
It doesn't, yeah.
but from her point of view, she's not moving at all. I mean, you can easily make an argument when you talk about this stuff that the center of my left eye has never moved my entire life.
Yeah.
Everything else has moved around it. So, from her point of view, those things are not, if they go off at the same time, the light should hit the middle at the same time, from her point of view, because none of it's moving.
You said that they wouldn't be the same distance for Peggy and Ryan, right?
Right, they,
We know that for Ryan, the left and right lights are equidistant from the detector. But because Peggy's moving, I guess, what's the difference in the distance between the lights and the detector for her?
the difference would be this ratio of gamma, depending on how fast we're making the train go. So if gamma, if the train is traveling at 99% the speed of light, then there's a factor of 7.089 between the two. So if one sees it as 10 meters, the other sees it as, well, let's do it the other way. If one sees it as 7.089 meters, the other sees it as 1 meter. Or I guess potentially 49 point something meters. All right, so if the light is green, so if the detector glows green, which light gets there first, red or left, right or left?
Right.
Yeah, right has to get there. So how on earth is it, from Peggy's point of view, that the right can get there first? Because from her point of view, if she has two lights that are equal distance from this detector, how can the right get there first? Because all of this is at rest relative to her.
Isn't it because green light's faster than red light?
No, they would be the same,
Okay.
same speed. Unless they're going through, well, we'll assume that there's a vacuum chamber in there, so we don't have to worry about diffraction of light and
Okay.
refraction of light.
So as Peggy's perspective, so the right light and the left light is moving backward relative to her.
No, relative to her, they're just sitting there. The train car is not moving relative to Peggy. The light, whatever these things are that flash, and the detector are not moving relative to her. And yet somehow the right light gets to the detector first. And the light's gonna be traveling the same speed. Alright, suppose I'm smack dab in the middle of the room, we'll just pretend. And I got a left light over there, and I got my right light over there, and there's gonna be a flash, and they get to some detector in the middle, and the stuff on my right side gets there first. How is that possible?
It's so confused for me. I mean, so confused.
Say it again?
I mean, I'm so confused.
Yeah.
Someone said, you said something feels funny?
I'm confused.
Oh, yeah, the relativity will do that.
You said that the detector was equidistant from both light sources?
Yes. Sorry, I'm going through puberty. Yes.
And the light's moving at the same speed?
Yes, it is. But somehow the right light gets there first. You are making an assumption that I'm trying to get you to not make.
Maybe.
I'm like 0 for 4 today, so I'm not gonna say that.
All right, yeah, let's review the facts here.
Is it something to do with time?
Yes.
Okay. We work on that for a minute. Give me one quick one.
Right, so the facts are that the detector comes out green, The fact is that Ryan says that and we'll assume that Ryan's not lying about this. Ryan says that the two flashes went off at the exact same time. And the left and right, and the detector, and the car, and Peggy are all at rest from Peggy's point of view. Go back to my scenario. I'm smack dab in the middle of the room. I got my left and my right side. Flash goes off. They're equidistant from me. The lights flash. If the one on the right gets to me first, then the light is traveling at the same speed coming at me. What has to be true?
Either time is sped up on one side or slowed down on the other.
There is another alternative.
Did the light bend or not take a direct path?
Direct path.
Direct path.
One side is getting, quote unquote, squished. The right side is getting, is contracting because of the speed at which it's moving.
Why would that be different than the other side?
Because, you're moving at a very high speed.
Not from Peggy's point of view.
I don't know.
All right, let's take this down to more Galilean level. You got someone on both sides of you, equidistant from you. They both throw a baseball at you at the exact same speed relative to the ground. The one on your right side gets to you first. Balls are ruled. So, what has to be true?
The one on the right was thrown before.
Yes. Back to this. What has to be true from Peggy's point of view?
That she saw it after Ryan already seen the green light. So.
No. Depends on what you mean by that.
I mean, because they're seeing the light.
Which one was which? The right goes off first, then it's green?
If the right hits the detector first, if the right light hits the detector first, it glows green. The
Okay.
detector glows green.
Well, from Peggy's perspective, that one would have had to turn on first.
That one would have what?
Had to turn on first.
Yes. Ultimately. They both go off at the same time from Ryan's point of view. They do not both go off at the same time from Peggy's point of view. The right light goes off first, and then the red light. This is the idea of simultaneity. Just because two events happen at the exact same time from one point of view, does not mean they go off at the exact same time as another point of view.
So that's simultaneity.
That's simultaneity, yeah. This is not talking about, if there's a lightning strike 5 miles away and there's someone 2 miles closer to it than I am, that person will see the light and and hear the thunder before I do. This is not what we're talking about. We're talking about that from a timing point of view, they do not happen at the exact same time from one point of view, even though they happen to another point of view. From a graphing point of view, if we think of this as time and position, and so two things happen at the exact same time. Sorry, try that one again. Position and time. So two things go off at the exact same time. And we made time is equal to 0. This plot right here starts to change as an object starts traveling faster and faster. And so my axes actually start to squeeze together so that if this is time is equal to 0 in the time t prime frame, this happened before 0, and this happened after 0. So in the blue frame, they happen at the same time. In the red frame, they do not. So as you think about the car and the barn problem, hopefully this gives a glimpse at one of the things that's going on here is that what's happening from the car point of view and from the barn point of view are not happening at the same time.
We're doing, for this one, this is reversed, right? We would be on the prime moving back to,
This would be Peggy's frame and Ryan's frame.
okay. Oh, okay. That's good.
Because they do happen at the same time from Ryan's point of view.
Yeah.
All right, questions to here? Now, I am about to go through a derivation. I'm going to do a couple derivations which are not exciting at all. And I thought about just jumping straight to the chase, which probably would be preferred, but then I've opted, I'm going to go through the derivation. Because this idea that things are not happening at the same time, not necessarily happening at the same position either. We need the math in order to come back to the car and garage problem, or what will eventually be pole and barn problem. Some people just can't handle the excitement, they have to step out, right? Yeah. Pause the video for a second. Probably should tell me I shouldn't say some things. And we're back.
I'm pretty sure you're gonna see my brains coming out of my ears. I can't believe one of your, well, then again, I've heard smart people have a good sense of humor.
Yeah, the person who came up with that term is now a professor at the University of Georgia.
That's even better. Like, the same, university that I've seen on some of your hoodies.
Oh, no, no. All right. So first, let's talk about invariance. Because we've already talked about that time is not the same for everybody. Length is not the same for everybody. Matter of fact, events happening are not the same for everybody. The order in which things happen. Is there anything which actually is the same for everybody? Well, there are two things at least. Speed of light. Speed of light is the same for everybody. So speed of light in a vacuum, if you want to narrow it down just slightly. So no matter how fast you're going, you would always measure the speed of light as the same. The other one, let's go back to our car traveling at some speed v, or this is the mirror here. And it shines the light on, hits the mirror, comes back. This distance here is h. So this travels some distance vt. And actually, do you want to do that in terms of x or? Yeah. Just. And so this is something like L. And so the light travels 2L in some amount of time t. that is the speed of light. So L is the hypotenuse of that triangle. So if we look at that, this is like h, this is 1/2 vt. Very similar to what we did when we were deriving time dilation. So the distance the light travels is 2 times h squared plus 1/2 vt squared. Over t.
Would it be the square root of that?
Yeah, thank you. Something was off there. Square root of that. So 1/2 ct is equal to the square root of h squared plus, oop, the 1/2 should be in the parentheses there, plus 1/4 v squared t squared. I am gonna make this x squared. Square both sides, I get 1/4 c squared t squared is equal to h squared plus 1/4 x squared. If I solve for h squared, I get h squared, and this is where we deviate from what we did before. H squared is equal to 1/4 c squared t squared plus minus 1/4 x squared. H is just the distance from the top of the box there to the mirror, and so it's just a number. It's a constant for our problem. So I'm going to multiply both sides by 4, and so I end up with 4h squared is equal to c squared t squared minus x squared. So that is just some constant. So no matter how fast this object's going, now 4h squared is some number. So if it were traveling at a different speed, say v prime, then this would be equal to c squared t prime squared is minus x prime squared. Or if we're traveling at a different speed, then they'd be double primes or however